So welcome to the session B of the Spark Summit. And this is the very first talk, and I'm delighted. So I'm Reno, and some of you know me as like the guy who wrote originally Shark, the SQL engine on top of Spark. I'm delighted to introduce Michael Armbrust here. Michael used to be a PhD student at the UC Berkeley AmLab, and after he graduated, he went to Google and helped design the next generation databases engine, otherwise known as F1 at Google. And at some point when we started Databricks, people started calling Michael and, hey, Michael, it's time to come back and design the next big thing for Spark. Now, here we go. Michael's going to talk about what he has been working on for a while, and it's going to be one of the most exciting projects going forward, I think, in the big data space, as well as in Spark.
OK, thank you very much, Reynold. So my name is Michael Armbrust, and I'm the lead of the Spark SQL project. Today, I'm here to tell you about kind of how we view Spark SQL as a unified way to access structured data through the entire Spark ecosystem. So to kind of start off by putting this in some context, let's first of all talk about what analytics used to mean, what analytics the old way was. Basically, you'd have a bunch of data, and kind of the canonical pattern is you put your data into an RDBMS. And there's a lot of benefits to this. The database guys knew what they were talking about. You get this high-level query language where you describe what you want, not necessarily how to retrieve that data. And the system automatically optimizes the queries for you. Unfortunately, there's some cons. The databases are black boxes. You have to kind of ETL your data into them, into whatever format they want. It turns out some analyses are really hard to do in SQL. I don't know if you've ever tried to implement machine learning in SQL. It's possible, but it's not necessarily the easiest fit. And then often, a lot of these traditional technologies just didn't scale. And so that kind of brings us to analytics the new way. This was originally MapReduce, but now it's Spark and all of these other systems. And the benefits here were instead of being trapped inside of SQL, you've got this full-featured programming language. And because of kind of the functional paradigm that is presented by MapReduce, you get easy parallelism as well. So now I can write my code. It runs nice on one machine, but it'll also scale up to thousands of machines, and I don't have to worry about doing that scaling myself. Unfortunately, this also isn't a panacea. There's a lot of problems here as well. And I think the biggest is that often it's difficult to do ad hoc analyses. Writing a MapReduce program is quite a few lines of code. It's not like typing a select statement into a SQL engine. And Spark makes that better with the Spark console. But still, sometimes it's nice to have SQL. And I think a key reason here is because when you write a program, the optimization is up to you. You have to reason about what data I need to read, what formats I'm going to be storing it in, if I'm going to use an index, exactly when to filter data out, and things like that. And so kind of a lot of the burden is put on you as the application developer. And so people figured this out as well. And there's been this trend of SQL on HDFS. So you can think systems like Impala or Hive or Shark. And kind of the idea here is instead of putting the data into an RDBMS, I'm just going to dump it in HDFS. And from HDFS now, I can run SQL queries. And this is great, because now, once again, I've got my high-level query language. And it's going to automatically optimize those high-level queries that I write. And some of the cons go away. There's no longer ETL. You can do analyses on data in situ. And it actually scales pretty well. But still, it turns out SQL is not kind of the only language that you want to be expressing your computations in. And this was really the motivation for Spark SQL. We wanted to kind of blend the ability to do relational query processing with your functional Spark programs as well. So this is a very young project. I actually announced it 6 months ago back at the Spark Summit 2003. And at that point, it was a single developer, me. It was about 700 lines of code, and we could run like 1 or 2 Hive queries. So let's flash forward to today. We have 44 contributors. We made an alpha release in the Spark 1.0 version. So if you're running Spark 1.0, Spark SQL comes bundled in, and you can try it out. We've got support for reading data from Hive, Parquet, and JSON. I'm going to talk quite a bit about that in slides coming up. And I think one of the really cool things is we have bindings in Scala, Java, and Python. So you can really use the SQL system alongside your existing Spark programs. And I think there's a lot of exciting effort. This is, as Matej said this morning at his keynote, this is one of the most active projects inside of Spark. So we're pretty excited about where we're going here. Just to give you an idea of like the high-level architecture of the system, it's actually broken into a couple of pieces. At the top of the stack is this thing called Catalyst. This is actually the first piece that I wrote. The idea here behind Catalyst is Catalyst actually knows nothing about Spark. It's just a relational algebra library for optimizing query plans. And basically what we do is when you write a query, we translate it into what's called a Catalyst logical plan. And then the system does a whole bunch of transformations on that to make the query execute more quickly. In fact, I had an amusing story where I was working with an engineer recently where he was running a query, and he's like, this is going way too fast. And it turned out the analyzer, the optimizer, was just figuring out that there was no answer to it and not running the query at all. So that's kind of the top part. And then from this framework, we actually built Spark SQL Core. And what this does is it allows you to execute these logical query plans as operations on RDDs. And this is kind of one of the, I think, a cool Spark success story. You can actually build a fairly full-featured distributed database in only 6 months because Spark does all of the heavy lifting for you. I'm just calling map partitions, and Spark is taking care of all of the kind of complicated work of distributing that processing around the cluster. And then this is where we actually have all of the different types of data access as well inside of Spark SQL Core. And then finally, we've got kind of a relatively thin layer, which allows the system to interact with Hive. And I'll go into more detail kind of in upcoming slides. So the elephant in the room here, or the shark, is what about Shark? So as Reynolds said, the Shark was one of the first projects to allow you to execute SQL on top of Spark. And the way that they did this was by modifying the Hive backend. So they took the original Hive optimizer, it produced Hive plans, and then they just wrapped each of those operators, each of those Hive MapReduce operators in Spark operators. And this was great because it actually made the queries run significantly faster, sometimes up to 100x faster because of Spark's ability to leverage in-memory computation. But the problems here were there was limited integration with Spark programs. So you were kind of writing in SQL or you were writing in Spark. And the Hive optimizer really wasn't designed. It was designed for MapReduce. So it's doing all of these things like trying to cram as many tasks as possible into a single map operation. We don't have to worry about doing that in Spark. Spark takes care of that for us. So what we did with Spark SQL was we decided to reuse the best parts of Shark, the Hive data loading code, the in-memory columnar representation, and then replace the rest. So we got this RDD-aware optimizer, which I talked about a little bit, and then these rich language interfaces for interacting with kind of imperative code alongside the relational code. So I'm excited to announce that basically the migration or the end of Shark. Basically, we're ending active development for Shark. But don't despair. We're only doing this because we believe that kind of Spark SQL is the way forward. And another thing that I'd like to announce today is that we actually now support all of the various interfaces to Shark inside of Spark SQL. So if you're using the JDBC server to connect Tableau or MicroStrategy or these other things, there's now a replacement for that. It's based on the same code. It just uses the Spark SQL execution engine instead. We're partnering with Simba to provide ODBC drivers for interacting with this. And there's also the command line interface. So if you've got analysts who don't like the Scala shell, you can interact with it in a pure SQL way as well. And so we've got a preview release that is available now. You can check it out. It's up there on GitHub. We just pushed it right now. So you can use it with existing Spark 1.0 if you want to kind of test out this preview release. And this will be a component of Spark 1.1. So when you download the Spark 1.1 distribution, which I think we're targeting sometime in August, it will come bundled with the JDBC server. So you'll kind of be able to use it right out of the box. So now that we've gotten that out of the way, let's dive into Spark SQL and kind of what makes it so cool. So a key part of Spark SQL is this notion of schema. So instead of just having these opaque objects, so with Spark, you can write these functional transformations on these collections of opaque objects. But all Spark knows is that I've got these people classes. It doesn't know what's inside. It doesn't know if there's kind of efficient parts of it that you're not using that we could throw away. And so as a result, kind of the thing that Spark SQL adds to standard RDD is this notion of a SchemaRDD. So it's got all of the normal features that RDDs have, but we also know the column names and the types of the data stored in there. And what this allows us to do is you can now express declarative transformations. So you say what data you want to retrieve, and we decide when we can filter things out, when we don't need to read certain data off disk, what the most efficient algorithm for doing a join is. Kind of all of that is taken care of for you. And it's because of this extra information that we have in the form of schema. It allows us to turn these objects instead into tuples. And this isn't an either-or proposition. You can actually go back and forth between RDDs and SchemaRDDs. So the way we're viewing this is kind of as a unified abstraction for working with data. So whether you want to write your data analysis pipeline in Python, Scala, Hive QL, Java, you can do it through SchemaRDDs, and you can access a wide variety of data sources using this unified API. So we have support for Parquet, JSON, Hive, and Cassandra. And we're also working on other integrations. Cassandra and SQL 92 are kind of future work, things that we would like to integrate into the stack as well. So how do you actually do this? I've got some data in an RDD. I want to turn it into a table. So one of the nice things is it's actually relatively concise to do that. So this is an example in Python. And I've got my standard RDD operations. I load in a text file. I split it by commas. I break it into parts. And all I need to do is create a Python dictionary, where the keys of that dictionary are going to be the names of the columns. And once I've created a new RDD that contains these dictionary objects, I can just pass it to a SQL context. And so I tell the SQL context to infer the schema. It looks at all of the columns that exist, and then creates a table. And once you've got this SchemaRDD or this table out, now you can all you have to do is say register as table, and it immediately becomes accessible to SQL functions. Just like everything else in Spark, all of this is lazy. I'm just providing the lineage or the transformation that allows this data to be viewed as a SQL table. So of course, Python's not the only answer. You can also do this inside of Scala. So in Scala, instead of creating a dictionary, you create a case class. So now you've actually got a type-safe way to define the schema of your table. And we basically use compile time Scala reflection to ask the compiler for the schema of that case class. In this case, we even support things like nested case classes. So if you've got kind of more complicated data that doesn't fit into a flat row, you can also put in repeated data types. So if you've got arrays or even arrays of case classes, all of that can be represented using the schema and then turned into a table. And finally, we also support Java. It's a little bit more code than the other two languages. But all you have to do is create a Java bean. And so you create a Java bean, you travel back to the 90s, and you can then load your data into Spark SQL that way. So that's getting data in. But now I kind of want to mix processing. So I want to kind of easily be able to move back and forth between my kind of full-featured programming language and SQL. And so this is one of the things that Ali really highlighted in his demo this morning. One of the features we're adding in Spark SQL 1.1 is this notion of language-integrated UDFs. So in a typical database system, when you want to create a UDF, you have to implement some class. There's a lot of boilerplate. I have to compile it into a jar. I have to upload that to the cluster. I have to hope that it got registered correctly. Debugging it is kind of difficult. In this case, just in your Spark program, all you need to say is register function. You pass it a Lambda function. This works in both Python and Scala. And that immediately becomes accessible. And we're reusing all of Spark's closure shipping magic to make that work. So it's kind of pretty easy to define things. And as soon as you do that, you can now use this function inside of your SQL queries. Another really kind of cool part about this integration that we're talking about is the ability to use some of the other higher level primitives that Spark provides. So take, for example, I've got a whole bunch of data. I've got a bunch of users and some demographic data about those users. But I also have an events table of actions that have occurred. Using these past actions and this demographic data, I want to predict which users are going to be likely to take some action in the future, so I can maybe target them for a campaign or something. So the first part of this sounds like something that SQL would be perfect at. It's going to be basically taking two data sources, joining it, pulling out the parts that I'm interested in. Maybe you'll even do some aggregations. So in this case, I basically just take the users table, join it with the events table where the users' IDs are equal, and I pull out all of the features that I want. But the result of this SQL query is a SchemaRDD. So no computation has been done. I haven't sucked all of the data back through JDBC back to my single machine or something. It remains distributed out in the cluster, and I can continue to do transformations on it using a higher level programming language. So in this case, I'm going to write a function called featureize, and featureize is going to take these rows and turn them into feature vectors. So basically what we're going to do is we're just going to pull out the action as the label of the point, and then we're going to create an array of the actual the features for each user. And once we've done this, it's now in the form to dump into MLlib. So I can take an off-the-shelf parallelized machine learning algorithm provided by MLlib. In this case, we're using logistic regression. And I can just dump that training data in and get a model out. So you've seen we've kind of mixed an off-the-shelf library, some custom processing, and extraction of data from an existing data source into a complete analytics pipeline. So one of the big parts of this is actually getting that data from these existing systems and pulling it into the Spark SQL ecosystem. So an incredibly important part of that is Hive compatibility. So I hinted at this a little bit. But basically what we have is we have interfaces to access data and code that exists in the Hive ecosystem already. So simply by creating a Hive context, you can now write your queries in HQL. We even support things like the transform clause, where you can have scripts executed as the result of your SQL commands. We get catalog info from the Hive metastore, so all you need to do is just drop your Hive site XML file into the configuration directory, and we'll automatically find all of your tables. We support reading data using all of the different Hive SerDes, even if you have custom SerDes. And then finally, if you've got existing investment in UDFs or UDAFs or UDTFs, we have wrappers that allow you to convert those into Spark SQL UDFs. You can kind of use them right out of the box. And this means that you can actually use all of the existing Hive UDFs as well. So even though this is a relatively young project, it's got kind of a fairly full-featured ecosystem of tools around it already. So working with Hive is pretty simple. Basically, instead of creating a SQL context, I create this thing called a Hive context. This is just a subclass of a SQL context that adds all of the extra Hive functionality. And once you've created a SQL context, all you need to do is use the HQL commands. You can actually run both SQL and HQL against your Hive data. If you use the HQL parsing interface, you can do DDL and stuff as well. So you can see in this case, I'm saying create a table or load data into that table. All of this is just passed directly back to Hive. So you should have kind of the full feature to create tables in exactly the same way as if you were sitting in front of a Hive console. And then finally, you can actually express the queries using HiveQL and get the answers back as a SchemaRDD. So Hive is only one of the data sources that we're interested in allowing people to access. And actually another kind of, I think, very important one is Parquet. And for those of you who aren't familiar, Parquet is an open source project. It's what Impala uses to store data. It's heavily used outside of Twitter. And Dave Patterson actually talked about it today. They're using it inside of the AMP lab as well. Do you have a question?
Yeah, ORC. Are you going to support ORC format?
Yes, anything that you can read with a Hive SerDes, you can read with Spark SQL.
Why you separated Parquet?
Because we wrote our own importer for Parquet that is much faster than the Hive SerDes for Parquet. And the other nice thing about Parquet is it's a self-describing storage format, so you don't need a metastore. So you can actually just point at Parquet files and get all of the column names out of it automatically. And that integrates nicely with Spark SQL. So I would say that's why I call this out especially. But you certainly can read ORC files as well. And so like I said, basically RDDs can be written to Parquet files, and you preserve all of the schema information. So Brian was talking about in the video this morning about TSV files from one system to another, not being sure if you were getting the columns right. This is kind of one of the things that we're trying to solve here. So I'm going to try to do a demo. Not as ambitious as Ali's demo, but something. Let's see. Sorry. They changed the settings. OK, here we go. So this is a kind of an extension of the data set that Ali used this morning in his demo. But what I'm going to do is I'm going to go down here and I'm going to kick off this SQL query. And let's walk through the pipeline that we actually use to process this. So this was a data set from a security research group at Berkeley. And basically what it was is it's 5.2 terabytes of JSON data stored in S3. So it's about over 5,000 files, each which has a gigabyte of JSON inside of it. And we're able to load it in using Spark. So we kind of use the standard Spark way of loading it in. We create a text file. We filter out blank lines because big data is almost always dirty, and so there's some corrupted stuff in there. And then what you can see is actually reading this data off of S3 takes a pretty long time. It's actually a fairly large data set. So even just doing the work of downloading it from S3 and decompressing it, it took over 10 minutes in this example. And that's not parsing the JSON. That's not doing any interesting analysis on top of it. It's just decompressing it. So one of the things that Spark SQL allows you to do is use SchemaRDDs, this kind of unified interface to move in between data formats. So I'm an analyst. I want to run a bunch of different queries over this data set. And so what I'm going to do is I'm going to try to convert it into Parquet. So what you can do is a new feature in Spark SQL 1.1 is going to be the ability to seamlessly load in JSON data from a text file. So you point this command JSON-RDD at an existing chunk of JSON data. We scan over it, we infer the schema, and we then convert that into a table. And so at that point, you can now take that table, and you could do queries on it directly. So let's say this is a one-time analysis. I don't want to pay the price of converting it to Parquet, because I'm only going to read it once. You could use that as a table, and you could run queries over it right away. But if I know that I'm going to be doing quite a few operations on it, I want something a little bit more efficient, I can actually then convert it to Parquet just by saving save as Parquet file. And what that does is it actually kind of writes it all out in this efficient columnar format. Once I've got a Parquet file, I can actually register it now as a table. So you can load in Parquet files, just like I said, very easily. Just point at the directory that holds all of them. We automatically infer all of the column names and data types. And then anything that you load in as a table can be registered, or anything you load in as a SchemaRDD can be registered as a table. So now that I've got that, I can actually kind of access it. So we'll do table last week. And this is going to give me a SchemaRDD. And if I want to actually see the whole schema of it, I can do print schema. I should give a quick plug. Yin, the guy who did the JSON support, is giving another talk in the third session today. So if you're interested in learning kind of more of the nitty-gritty details about our JSON support, you should go to his talk. But you can see it actually fully inferred the relatively complex schema of this JSON data set. So Twitter actually puts all sorts of information in there. We maintain any nesting that occurs. We support arrays that exist inside of the JSON. All of that can be represented. And the really cool thing here is even though this data is still stored in S3, even though it's something that I couldn't fit in the memory of this cluster, we're now able to do operations over it significantly faster. So in this case, I did a count star, and it finished in 30 seconds. So that's 10 minutes to just decompress the JSON data down to 30 seconds for running a trivial query. But trivial queries aren't particularly fun, so let's try to do something a little bit more complicated. And so what I can do here is this is the UDF that Ali used this morning. I'm going to register this function hour of day, which uses everyone's favorite time parsing library, JodaTime. And now I'm able to run this query. And you can see this aggregation query reading 5,000 files off of S3. This is not cached in memory. Took just slightly over a minute to execute. Yes? Oh, this is the Databricks cloud platform that I'm showing here. So limited beta coming soon. Sign up on our website. So, yes?
The Parquet support in the Spark SQL itself, maybe there's a problem, but the projection pushdowns and all that were not working.
OK, come and talk to me afterwards. Because they're working in some cases. So that query would have taken very long, but I'd love to fix any issues you're having. So in this demo, I kind of showed how you can take JSON and turn it into a SchemaRDD, turn SchemaRDDs into Parquet, and turn those back into SchemaRDDs. And then you can execute SQL queries, Spark jobs, UDFs against any of those. So I'm running out of time, but I really quickly want to talk about performance. So it's not just about converting data into more efficient formats. We've actually been doing a whole bunch of cool things with expression evaluation. So this is a preview of what's to come in 1.1. For those of you who have tried to write a database before, expression evaluation can be incredibly expensive. You have virtual function calls, you're branching based on expression type, you're creating a lot of objects on the JVM. So as a quick example of why this is so expensive, let's look at just evaluating a plus b. So I've got a query, I say select a plus b. What's actually going to happen on the JVM when you interpret this? Well, you're going to start off by calling the eval function on the top node in this tree. So we've created this expression tree to represent it. We call eval on add. It's going to then make another virtual function call to its child. Say, OK, now you give me your value. That's going to return a boxed integer. So we're actually allocating an object there in order to hold that value. We're going to make another virtual function called a b to get its value. That's going to return another boxed value. And then we're actually going to do the work. We're going to do a single integer addition operation. That was what we actually wanted to accomplish. And then we're going to box again. So that was pretty expensive. I think we can probably do better. And we're doing that with this really cool feature that they just added in Scala 2.10 called runtime reflection. So instead of interpreting this code, what Spark SQL is going to do is actually going to generate bytecode at runtime for the specific expressions that exist in your queries. So this is kind of just a really simple example of how we're doing it. But you can see we're doing pattern matching here on attribute. So when we see an attribute, we're going to generate the code for actually retrieving that attribute. And then you see these things that look like strings. But they start with the letter Q. That's called a quasi-quote. And so what a quasi-quote is it's not a string. It's actually a piece of Scala code. And the result of that block of code is actually a Scala AST. So I'm actually getting back the abstract syntax tree for this program. And the really cool thing about the way quasi-quotes and reflection work is Scala makes it very easy to splice these together to create the entire evaluation operation. So we've got add here. It just recurses on its child to get the left value and the right value, splices those trees in, and adds up the result. And so what you end up with is code that looks significantly more like this. We have two operations to get the data out of the rows. We store those into primitive values. We store the result in also as a primitive value, and then we rewrite it back into the row. And the key here is there's fewer function calls, and there's no boxing of primitives. So it's actually quite a bit faster. And this is actually a well-known trick. Database people have known for years that code generation makes your queries run faster. So we're not novel in that regard. What's really cool here is that Scala reflection and quasi-quotes made this a very easy thing to add to our system. So a combination of the Catalyst optimizer, some of these cool language features that we're using, mean that this was kind of an experiment that we started over a weekend and had amazing performance results instead of a major overhaul of the system. In fact, the initial version was only 1,000 lines of code. So that means that our code generation is actually quite extensible. So we plan to kind of hard code in as many of the different types of expressions that you evaluate commonly in SQL. And it's very easy for kind of you as developers to contribute back to this system as well. So we've got to have a performance microbenchmark to see if this works. So I'm going to try to evaluate a plus a plus a 1 billion times. And so if I do this the naive way using the interpreted evaluation, it takes quite a while. If I sit down as a pretty good Scala programmer and I write down custom Spark code to do this as efficiently as possible, I can get it to be this fast. So now it's down to under 10 seconds. Using Scala reflection is almost exactly the same. So you can get hand-coded performance just by writing SQL queries. So I'm almost done, but I want to talk just kind of a brief overview of the features that are slated for the 1.1 release. So we're hoping to include this code generation patch that I'm talking about now. We're definitely going to have these language-integrated UDFs, which I showed off and Ali showed off during his talk this morning. We're working on we've added broadcast join, and we're working on kind of automatically selecting when that's the right thing to do using cost estimation. We're going to have support for JSON and nested Parquet. And finally, there's been a whole slew of performance and stability improvements. So if you're still running 1.1, you should definitely check out, or 1.0, you should definitely check out 1.01 because we've been hard at work. And here's just a real quick preview of the performance. This is a comparison of Spark SQL with the CodeGen patch in a development branch compared to the most recent release of Shark. And so you can see in all cases it's a little bit faster. And for some of the more complicated queries where there's a lot of expression evaluation, we're actually seeing an 8x speed up over Shark. So we're pretty excited about the possibilities for Spark SQL. And so that's the end of my talk. If I have time for questions, I'll take a couple. One question. Anybody? Yes. So all of the, yeah.
While Michael's answering a question, can the guys from data stacks come up to the stage. Oh, here.
Yeah, so Spark and all of its components are released in lockstep. So Spark SQL 1.1 will be released with Spark 1.1. The current target for that is August. And all of the details about the timeline and code freeze and all of that are on the Spark website. So yeah, check that out. And we'll be posting to the dev list kind of as the development schedule progresses.
So replacement of the Shark shell will be in 1.1 or the...
It will be in 1.1, but it'll also be in this preview release, which I put the URL up for. So you.
101, 102, or whatever.
Yes, that's a good question. So it's definitely not going to be in 101 because we've already cut that release candidate and we don't want to cram any more features in. In terms of 1.02, there's a question of whether or not it's OK to cram a giant feature into a maintenance release. We really want people to be able to upgrade without being afraid that we're going to break things. And so we're pretty hesitant to put that in there. But the branch that I put up there is compatible with 1.0. You can use it on 1.0 clusters. Yeah, so I would definitely check out that branch.